So what do we need to do to execute an instruction? Well, we need to go figure out where the instruction will come from in main memory. So that's determined by the program counter. So we'll have a special register called the program counter. We'll take the value of the program counter and send it over to the main memory as an address. And the main memory, some number of nanoseconds later, will provide us back the 32-bit instruction that lives at that address. And here we can see a particular 32-bit instruction here. We'll need to look at the opcode bits to figure out what to do. We'll need to be able to read a couple operands from the register file. In this case, we'll need to be able to read R2 and R3. Those are the 2 and 3 here are indicating which register we want to read. We'll need to be able to do an add. And then finally, we need to write the result back into the register file at register 4. So we need basically the hardware to do all of that. Let's start with figuring how we're going to do instruction fetch. This is pretty simple. We have a 32-bit register. Why does it say 00 at the bottom? What is that telling us? Where did that come from? I'm sorry? It's a multiple of 4. So remember that, sadly, we are using byte addressing, even though we're always fetching words, 32-bit words. We actually, so groups of 4 bytes from memory. We always fetch them from a mod 4 boundary. So in other words, 0 mod 4. So we can fetch information from location 0. The next word location in memory has the byte address of 4, and the location after that has the byte address of 8. So the program counter, which is always fetching entire words from memory, or always pointing to entire words in memory, will always have its bottom 2 bits to be 0. So that's that 00 is sort of reminding ourselves of that. So the program counter holds the address of the current instruction in main memory. So we take that output and we simply feed it into the address port of our memory system. So we have a black box, which is takes in an address, and some number of nanoseconds later returns the 32-bit data, which is found at that address. And then we go ahead and use those bits, those 32 bits that come back that represent our instruction. We'll use some of those bits directly as they come back. Well, some of our things like the register numbers we need, those we'll use directly, no processing needed. We can take the actual bits from the instruction and simply feed them to the right wires, for example, in our register file. However, we will take the opcode, the 6-bit opcode, and we're going to run it through this control logic, which is, think of it as just a big read-only memory. It has, well, at least in this diagram, it would have 64 locations because we send in 6 bits. So that's and with 6 bits of information, there are 64 combinations. So depending on which of the 64 opcodes goes into here, we're going to develop a set of control signals. And that'll make more sense in just a second. As you start seeing what the control signals control, I hope all that will be clear. And then finally, what happens while we're executing the instruction, we're also adding 4 to the program counter. And at the end of the cycle, we will be loading the program counter with the next program counter, the new program counter, which in terms of our very simple execution right at the moment is always the next instruction, that 4 bytes farther along in memory. Is there any questions about sort of the instruction fetch? And we're about ready to fill in all the interesting stuff that actually do the execution of the instruction. Yes?
I'm confused as to why PC is multiples of 4 and how come the control logic isn't. I thought there were 5 bits sent to the output.
Well, bits 26 to 31 is actually 6 bits. 26, 27, 28, 29, 30, 31. So does that help?
Right, why isn't it 5?
Why isn't it 5?
Yeah.
Oh, you mean, so you're thinking about the control signals that go into the ALU, which were 5 bits of control signal. And those will clearly be information that we're going to have to generate from the 6-bit opcode. Okay, but the opcode in the instruction is not the same thing as the ALU control signals. And we'll discover that the 5 ALU control signals are only some of the control signals that we'll need to generate from the 6-bit opcode. And you would say, well, couldn't we pick a clever encoding so that the 5-bit ALU field was exactly somehow embedded? And we've chosen not to do that, but that's maybe with a cleverer choice of encodings we could have simplified the control logic. I think you'll discover the control logic if you actually didn't implement it as a read-only memory, but instead implemented it as just a bunch of discrete logic. That discrete logic is actually only a handful of logic gates, so it's not very complicated. The transformation from opcode to ALU function code is actually pretty simple. Why is a PC a multiple of 4? So just to reprise our sort of apologia about byte addressing. So we use byte addressing. In other words, we think of each 8-bit quantity in memory as separately addressable. So each one has a unique address. Because we actually are building a memory system that only fetches 32-bit words, the load and store instructions always fetch a 32-bit quantity, we will always be sending over an address that points to the low order of the 4 bytes we want to actually fetch from memory. So we'll always be fetching 4 bytes at a time. And by convention, we always choose to fetch bytes at a 0 mod 4 address. So we'll fetch a word from location 0, and from location 4, and from location 8, and from location C. So I'm just counting up in hex, counting by 4. Any other questions? Yes?
So what's the total size of the memory that we're incrementing by 4 to get through?
Okay, so what's the total size of the memory? Well, we see here that we're actually sending over 32 bits of address. So how many bytes would that be? How many different combinations of address bits are there? 2 to the 32, which is 4 billion. So it's a 4 billion byte memory, or a 1 billion word memory. For many years, that was sort of a very standard sort of size. Almost all the machines that you have now are 64-bit machines, so they can address considerably larger amounts of memory. But for us, we have a very simple machine, so 4 billion bytes is sort of what we can address. Other questions? Okay.